All right, this is lesson 1 of the Pythagorean Theorem unit. We're looking at squares and square roots today. So first thing we're going to be talking about, this lesson's kind of in two parts. The first part is all about perfect squares. Let's just have a look at the structure of this lesson. We're going to be determining whether certain numbers are perfect squares or not. And then the second part of the lesson, we're going to be looking at square roots. We're going to be evaluating them and then estimating them. Okay, so perfect square. A perfect square number, when you have a perfect square number of objects, you can arrange them into a square. So for example, I'm going to give you an example first before I define it. So an example is 4. If I have 4 objects, I can arrange them into a perfect square. We can also write 4 as a product of 2 times 2. Let me give you another example, 9. If I have 9 objects, I can arrange them into a square. And 9 is equal to 3 times 3. One more, 16. 2, 3, 4, 5, 6, 7, 8. I can arrange these 16 objects into a perfect square, and 16 is 4 times 4. So you might notice a little pattern here. Perfect square numbers can be written as multiplication or product of 2 identical numbers. So 25 would be another perfect square because it's 5 times 5. So perfect squares can be written as a product of 2 identical numbers, or factors, I'll say. Okay. Also, the word, we call it square because it's literally in the shape of you can arrange these numbers into squares. Okay, we're going to learn 2 ways of checking if a perfect square is, or a number is a perfect square or not. First thing we're going to do is do a factor tree. I'm going to just do the first 2, and then I'm going to leave you to do the second one, and then same with the guess and check. Okay, so 196. So when you're making a factor tree, you're trying to divide by numbers that go into, you're trying to find factors of 196. So one thing I can think of that divides nice and evenly into 196 is 2. And you don't have to start your factor tree the same way as me. You'll actually end up with the same endings anyways, no matter how you start. So you could start by dividing by 4 or 7, it doesn't matter. But when I divide by 2, I get 98. Okay, so 2 times 98 is 196. And I check if I can go further on any of those branches. We call it a tree because it kind of has these branches. 2 is a prime number. I can't go any further with 2. It can't be divided anymore, except for by itself. But 198 I can divide by 2, and I would get 49. 2 I can't divide anymore, but 49 I can. I get 7. I divide by 7, and I get 7. Now 7 and 7 are both prime as well. So we have these endings of our branches, and they're all prime numbers. And actually, if you multiply these, 196, if you multiply 2 times 2 times 7 times 7, you'll get 196. Each number has its own prime factorization, and it's unique to that number. Turns out, if you can group these prime factors into 2 equal groups, we can put 1, 2, and 1, 7 together, and then a 2 and a 7 together. So 2 times 7 would be 14, and 2 times 7 would be 14. 196 is 14 times 14. That means it is a perfect square. Because 196 is 14 times 14. So it is a perfect square. Okay, let's try the same thing with 250. So we can divide it by 2. Again, you don't have to start that way. No matter how you start your factor tree, you'll always end up with the same endings. But when I do divide it by 2, I get 125. And then I can divide by 5. I get 25. These are prime numbers, so I'm going to circle them. And then 25 I can divide by 5. These are prime. I can't go any further with these. So 250 is equal to 2 times 5 times 5 times 5. And if I try and put those numbers into 2 equal groups, I can't. So this is not a perfect square. If I had 250 objects, I could not arrange them into a square shape. Because I can't arrange the prime factors into 2 equal groups. Can't go 2 equal groups. I'm not going to do the factor tree for 64. You could try it on your own, but what you'll see with 64 is that you should end up with 6 2's. 64 is made of 6 2's, and these can be formed into 2 equal groups. 8 times 8, 2 times 2 times 2 is 8. So 64 can be written as 8 times 8, and so the result is it is a perfect square. So if you had 64 objects, you could arrange them into a square shape, and the side lengths would be 8 by 8. All right, you can also use a guess and check method to figure out if something's a perfect square. You just try and guess numbers that might multiply to make that number. So for 256, I already know 14 times 14 is 196. So I'm just going to guess like 15 times 15. I know that this is not true because that'll end in a 5, but 225, that's a little too small. Let's try 16 times 16. 256, great. I got it. So because the number can be written as product of two identical numbers, it is a perfect square. The guess and check method can be a little faster. 315, let's try and get 315. I already know 16 times 16 is 256. Let's try 17 times 17. That's 289. No, too small. Let's try 18 times 18. You get 324, too big. There's nothing in between 17 times 17 and 18 times 18. So 315 is not a perfect square because I can't write it as a product of two identical numbers. Let's try 484. I'm just going to take a wild guess and go 22 times 22. Seems like kind of symmetric. Oh yeah, it is. 484. So 484 is a perfect square. Okay. All right, now let's go ahead and look at, it's almost the opposite of what a square is. It's a square root. So the square root is essentially if you have like a square with like 9 objects, or the area is 9, a square root is asking for like the side length of that square. So like what times what would equal 9? So the square root of 9 would be 3, since 3 times 3 equals 9. Okay. So if you had an object made of 9, or a square made of 9 objects, the side length would be 3. So the square root of 16, for example, would be 4, since 4 times 4 is 16. Now, when you take the square root of perfect squares, it works out to a nice answer, but what you'll see in a second is that when you take the square root of a non-perfect square number, we're going to have to estimate it. Okay, so let's evaluate these square roots. Square root of 9 would be 3. Square root of 36 would be 6, since 6 times 6 is 36. Square root of 64, 8. Square root of 100, 10 times 10 is 100. 144 is 12. Okay. 22, however, we can't really evaluate that. There's no whole number that multiplies perfectly to make 22. Like if I tried 4 times 4, I get 16. And if I try, so the square root of 16 would be 4. And if I try 5, I get 25. So it's going to be somewhere in between 4 and 5. We call these benchmarks. They're going to help us estimate what square root of 22 is, and it's going to be a little closer than square root of 20, little closer to 5 than it is to 4, because 22 is a little closer to 25 than it is to 16. So let's just make a guess, and we're going to guess, maybe let's try like 4.6. Okay, we can use a calculator for the multiplication, but what we don't want to use the square root button on our calculator. So we get 21.26. That's a little low. Let's try a little bit higher. And when you're doing these, I would like you to write out all of your steps and what you're guessing and what you're typing into your calculator. It's a little high, but it's better than 4.6. It's pretty close to 22, actually. So what we're going to say for our final answer, and it says only the nearest tenth, so we're only doing 1 decimal place. If I needed to get like a closer estimate, I could add more decimal places on, but we're just going to go to 1 decimal place here. So we say it's approximately, that you can do these little squiggly equal sign to say we're estimating here, it's not exact. 4.7 was the best estimate. and that's our final answer. So this is how your work should look when you're estimating your square roots. Okay, so that is the end of the lesson.